All right, well, hello and welcome to this month's Power Hour, where we're going to be talking about forced air induction diagnostics. We're specifically going to really lean on some of the most common issues you'll see coming through your shops when it comes to turbocharged vehicles. And we kind of have to have this conversation at this point because of the amount of vehicles on the road with a turbocharger. You know, to kind of put it in perspective, if we go back to even 2010, only about 10% of all vehicles coming off the assembly line had a turbocharger. Well, now we fast forward to 2025, about half of all vehicles coming off the assembly line now have a turbocharger. So whether you see a lot coming through your shops today or you see very little, the reality is in the very near future, a lot of turbocharger diagnosis are going to have to be done in every one of the bays across the United States here. So what we want to do is we want to cover a couple of the most common diagnoses you're going to see. We're also going to look at some scan data, show you a couple things you can look at that might lean you into the right direction of what might be going on with the turbocharger and why it's not operating the way it should be. We're also going to go, and I've got a couple things on the bench over here, and show you some pretty quick and easy manual things you can do to try and get a diagnosis done without having to tear the entire system apart. That's really what our goal here is to not have to tear everything apart just to get a diagnosis done. So that's what we're going to be looking at today. And again, thank you for being here. Welcome to the Power Hour. And I'm going to head over to the bench so we can get into some of the content that I know is going to be more important than me standing right here. So I'll see you over there. All right, so again, today's topic of conversation, diagnosing forced air induction or turbocharged systems. Now, before we get started, you'll see we've got a full turbocharger kit here that's laid out. This is here for a very easy and specific reason, and that is to say, if you have to replace the turbocharger, you've done your diagnosis, we know there's no saving this system. We've got to replace the turbocharger. If you order a kit like this, you need to make sure you use everything in the kit. It's there for a reason. It's been identified as you may have to replace it anyway. It's probably going to break in the process, things like studs, or there may be an update to a component within the system that is so mandatory that we can't get around not doing it. Things like on this Chevrolet Cruze, I'm sure you've done any of these turbochargers before, you know, the supply line for the oil to the turbocharger had a known issue, and that was it was easily clogged. This is the updated design, and the last thing we want to do is replace a turbocharger, put that old design back on, and end up starving the new turbocharger after the repair is done. Doesn't make any sense. So whenever we do get a kit, make sure we use everything in there. We're going to be sealed properly. We're going to have proper oil supply to the turbo, and everything's going to mount up the way that it should. So that's just one point to make here. The other, you see, we've got a couple of different demonstrations that we're going to do back here in the back. And of course, we've got our charge air cooler or our intercooler just kind of in the background here just to kind of feed into the entire system here and say, hey, these are the things that we're going to be dealing with most commonly when it comes to turbochargers. So with that, let's jump into it here. And we're going to, again, do a kind of a quick rundown of the most common components that you're going to be looking at, diagnosing, and how the turbocharger works as a whole. So again, before we get into the diagnostic piece of it, let's again just look at the most basic level of what a turbo consists of and the system consists of. So remember, at the most basic level here, a turbocharger is going to consist of just three major components: the turbine, the compressor, and the bearing system that's going to support the turbine shaft. And that's going to connect the turbine and compressor wheels together. So it's really just three major components there. And then that turbine wheel is going to be responsible for converting heat and pressure into the rotational force. We've got the high pressure from the exhaust manifold that's going to always seek low pressure. And as the exhaust exits the cylinders and flows to the exhaust, it's going to spin that turbine and convert kinetic energy into rotation. And as that turbine wheel rotates, it of course is then going to spin up the turbine shaft, which is in turn going to spin up the compressor wheel. Something to note here though is remember, turbine wheel selection is going to be critical to a properly built turbocharger system. So when we see these turbos coming on different manufacturers, we'll see them a little bit smaller, a little bit bigger. It's because of what they're trying to achieve. And they have to be very specific, because if we have too small of a turbine wheel, we can induce excessive back pressure and choke the engine up, of course making it lose power there. And then on the other hand, if we select too large of a turbine wheel, it's going to result in increased lag and make it a little bit more difficult for the engine to achieve its targeted boost numbers. So just an important note there, there's a reason that the size is the size. It's been very over-engineered in most cases to make sure that it's going to hit the targets that it's looking for. Now, with that said, we understand that the turbocharger works by compressing air, right? We're going to be spinning that compressor wheel. It's going to be compressing air, and that's going to create a lot of heat, right? And that's why it's important that we have an intercooler. We saw that behind me just a moment ago. Intercooler, charge air cooler. These are super important because of the amount of heat that is created. It's simply the law of thermodynamics, and it's present really in any turbocharged engine application, even on low boost settings. So we got to remember that even on low boost, we're still going to have that heat. So the incoming air charge has got to be cooled down before it can enter that intake manifold. And the most common method is the intercooler. Now, the intercooler is nothing more than a heat exchanger, just all we have to remember. And its job is to remove heat from the intake charge that was created by compressing it. So if you understand how a radiator works, you understand how an intercooler works. It's just like that. It's an air-to-air intercooler. Works by passing hot air from the compressor through a series of tubes, which are going to be physically connected to a series of the aluminum fins. And then as ambient air passes over the intercooler surface and the thin fins, it's going to draw heat away from the compressed air, which provides the cooling effect. All right, so let's get into what we're really going to be spending a lot of time talking about here. So again, we've got the basic components of a turbo. We have our intercooler, but all of our turbos are going to have a wastegate system of some sort. Now, a wastegate is simply, it's just a device that bleeds off exhaust gas before it reaches the inlet of the turbine housing, right? So if a turbo system did not have the wastegate, if it didn't have a wastegate system at all, the turbine would basically see all of the exhaust throughout the engine's operating range, and boost would continue to rise uncontrollably until either the throttle was shut or the turbine wheel reached its choke point. Now, for most engines, this would create an excessive amount of boost or airflow and destroy a lot of parts. We definitely don't want that. So, to control boost and the engine power, these turbo systems are going to rely on wastegates, which are going to be mounted before the turbine housing or inside of it in the case of say an internally gated turbo, and act as a controlled bypass for a percentage of exhaust gas to regulate turbine speed and boost. And of course, there are various design differences in wastegates. There's a couple different types out there, but if we think about it in the most simplistic terms, every wastegate is going to feature an inlet and an outlet port to which the exhaust gas can enter. It's got a valve that regulates the flow of exhaust gas through the inlet port. And it's going to have a spring diaphragm actuator, which is going to control when the valve opens and closes. Now, under normal driving conditions, the wastegate valve is going to remain closed, and all the exhaust gas is going to be sent directly to the turbine housing. Now, as boost pressure rises, pressure is going to act upon the spring assembly and begin to lift the valve. And that's going to divert that exhaust flow away from the turbine, and it's going to control the turbine speed to regulate that boost pressure. This is our way of making sure that we don't have uncontrollable boost throughout the operation of the vehicle. And now with a basic turbo system like we just looked at, we're going to have a pneumatic actuator that's going to control the wastegate valve opening. Now the wastegate is going to open when the boost pressure exceeds the spring tension. Now since the engine control system can monitor a whole lot of inputs, things like the engine knock, intake air and engine temperature, and manifold pressure or boost, the boost pressure can actually safely be increased above the spring tension of the wastegate with some computer controls. And so the turbocharger wastegate is going to be controlled by the PCM through a wastegate regulating valve solenoid, and this solenoid is going to be pulse width modulated, and it allows some of the boost pressure to bleed to atmosphere, keeping the wastegate closed. And now keep in mind here, this image is actually only showing a pressure controlled wastegate, which is where the wastegate moves when the pressure is applied to the actuator. But we got to remember that the wastegate, remember I said there's various designs. It can be pressure actuated, vacuum actuated, or electric motor controlled. Now an example of a vacuum actuated, we've got the 2-liter EcoBoost, which was introduced with a vacuum actuated wastegate. And this is going to use a bypass valve on the compressor to regulate the incoming boost. We'll talk about bypass here in a second. Now this can assist in the control of the wastegate position at all engine conditions. The wastegate can be opened at some partial load conditions to reduce the back pressure on the engine, and this is going to reduce the pumping losses and improve efficiency and fuel economy. So it just depends on the manufacturer and what they're trying to accomplish, whether they're going to use pressure or vacuum operated or whether they're going to use a bypass system. And we won't spend as much time talking about electric wastegate actuators here today, but it is good for you to know that since about 2017 here, They have been being applied to different vehicles, primarily Ford, using those in the 3.5 liter F-150. So again, you're not going to see as many of those coming through as you would a vacuum or pressure operated, but it's a good thing to know that they're out there, and they're probably going to be adopted just as much as turbos have been adopted by all manufacturers at this point. All right, so we've discussed a little bit about some of the different types of wastegate actuators, and I told you in the beginning here, we're going to talk about some manual things that we can do without tearing the entire system apart that might actually help us in a diagnosis. And to help me show you that, I actually have my buddy Mark here. He's one of our trainers who's going to give us a little bit of a rundown on some things that we can do along with scan data to try and verify proper functionality and operation of the wastegate and the wastegate actuator, again, without having to tear everything down. So Mark, I appreciate you being here. I'm going to switch the camera over to you and let you show us a little bit of knowledge that you have and you've been showing us for a while here.
Well, thanks for that, Corey. And I'm glad to be here and helping out today for this Power Hour. So what Corey was talking about is how can we a little bit more effectively or easily diagnose some of these turbo issues that might come up. Well, we have a vacuum actuated turbocharger here and we have a pressure actuated turbocharger here. And if you'll notice, but on both of these, the wastegate is closed. What that means is when the engine's running, you have boost, period. If you don't want boost, then something has to step in to remove that boost. How does that happen? On a vacuum actuated wastegate, obviously we have to apply vacuum to it. On a pressure actuated wastegate, we have to apply pressure to the wastegate. But where does the pressure come from? Well, the pressure comes from boost. Remember, it's always on. So we always have even just a little bit of boost at idle. How does that work? Well, their system will apply pressure to the wastegate actuator, and as we apply it, you can see the wastegate actually move and open. Now, you might be saying, but that's a vacuum pump. Yes, it is. This side's vacuum. This side will apply pressure. So we switched it over so we can apply pressure to the wastegate actuator so that we can test it. And in this case, if we watch the actuator arm here, you can see it move. Now this is still going to be on the vehicle, so you're not going to be able to see down in here the wastegate itself, but you can at least determine, okay, the wastegate actuator solenoid arm is all working correctly. Well, that's great, Mark, but what about the inside? How do we know if the inside is working? Well, this is where your scan tool is your friend. With your scan tool PID selection, you can select map sensor, you can select boost pressure, and different pressures to see if they change. Now remember, you're supposed to have even a slight bit of boost at idle. If I actuate this wastegate actuator and that wastegate opens, you should see even a slight change in pressure. If you don't see that pressure, or you don't see that pressure change, rather, that means that, okay, now I've got to go a little bit further, tear maybe the exhaust downpipe off of it if it's not too difficult to get to. But at this stage, let's pause for a minute. Our whole point here is we want to get across the finish line. Now, let's not confuse getting across the finish line with getting the vehicle repaired. Because remember, getting the vehicle repaired is up to the customer. So at this point, you could call the customer and say, look, we've done some diagnostics. We see your turbo issue. We've pulled codes and we've tested it, and we're finding that the boost is not changing. That means we have to tear the turbo apart. Would you like us to go ahead and proceed further with the understanding that we're probably looking at a turbocharger assembly? And if they say no, guess what? You can cross the finish line. What do I have to do to put this vehicle back together so that I can get it back to the customer? Watching the wastegate, watch it move closed, put my tools up, button up whatever I need to under the vehicle, pull it out into the bay. We have crossed the finish line. The vehicle's not repaired, but it has been diagnosed properly. All right, now on a vacuum actuated, it's just the same thing in reverse, okay? We're just taking vacuum, we're applying it to the wastegate actuator because we have boost, we don't want boost, and we apply vacuum after we close the vacuum pump. There's our actuator moving. Easy peasy. Now this is on vehicles where you can fairly easily access this, again, using your Mighty Vac vacuum pump. Very easy and simple. All right, and with that, Corey, we'll hand it back over to you.
Fantastic. Thank you, Mark. Yeah, that's just one of those things where it gives us an opportunity to, without tearing everything apart, just make sure that the wastegate actuator is at least working. Now, if we don't see the changes that we're looking for on the scan data, again, like you said, we need to go a little bit further. We're going to have to tear some things down. But fortunately, in this case, if we did have the scan data matching what we were doing, like you just did with the hand pump, at least we know we can eliminate one piece of the diagnosis and move on to something else.
That's exactly right, Corey.
All right, well, let's get back to the presentation here. And Mark, I'm coming back to you here in just a second. So
all right, I'll be here.
All right. And so now that we have a little bit better understanding of how the pressure actuated and the vacuum actuator works, let's see what it looks like when we add a bypass into the system. So again, we know the wastegate is used to control the amount of boost generated, and inside the wastegate actuator is that spring that causes the wastegate actuator rod to pull the wastegate closed. Now this is going to be in the default position, full boost. However, if during boost operation, the throttle is suddenly closed, that boost pressure will be high in the turbocharger with little to no airflow. Now this can not only cause a lot of damage to the turbocharger, but it can also produce a lot of unwanted noise as well. And so here's where systems will use a bypass valve to dump that boost pressure during these kinds of situations. So let's zoom in on the wastegate control and see what that looks like. So we got the wastegate connected to the actuator with a rod, and inside of the actuator is that diaphragm and spring. The spring applies the internal pressure in order to pull on the actuator rod, effectively closing the wastegate. Now on the other side of the actuator diaphragm, it's going to be exposed to the boosted pressure generated by the compressor. And so as that boost pressure rises inside of the actuator, it applies pressure that tries to push the actuator rod outwards, which would cause the wastegate to open up. Now there is essentially here a tug of war between the spring and the boost pressure to control the wastegate. And the PCM controls the amount of boost pressure applied to the actuator by bleeding off some of that boost pressure back into the inlet side of the turbocharger. So in this example here, we see the PCM is bleeding off just enough pressure so that the spring wins the tug of war and the wastegate stays closed. However, in this example, we can see that the PCM is controlling boost pressure by allowing enough boost pressure to be applied to the actuator for the pressure to win the tug of war with the spring, and then that's going to open the wastegate. And that bypass valve is going to control a large passage joining the inlet and the outlet side of the compressor. You can see here, we've got the bypass inlet, which is on the non-boosted side of the system. And then on this side here, we have the bypass passage on the boosted side of the turbocharger. This is really being taken care of with, in most cases, a very simple bypass valve. And that bypass valve is going to contain a rubber plunger. It's going to have a diaphragm. It's going to be exposed to the engine vacuum. And then it has a spring. And the function of that spring is to push the plunger into the position to block off the bypass passage. Now, at the desired time, the PCM will apply vacuum to that diaphragm by energizing the bypass solenoid. And this is going to cause the plunger to lift and allow that passage to open so that the boost pressure is dumped. All right, so there's our brief description of how the bypass valve system works, or the bypass system works as a whole. Is there a way we can manually test these bypass valves similar to how we tested the wastegate actuators a minute ago on the actual turbo? Well, in some cases, yes, there is. Not all of these are serviceable, unfortunately. Not all of them are easily accessed, unfortunately. But in some cases, we can actually service or test these bypass valves without, again, having to tear the entire system down. So to give you a better close-up shot of what that looks like and how the bypass system works, outside of just something on a screen, I'm going to send it back to Mark here. Mark, I see you've got everything laid out in here, so it's on to you. Tell us a little bit more about these bypass valve systems and things that we can do to try to get some of that manual testing done.
All right, Corey. So here's what he's talking about with the bypass valve. And as you can see, there's a port, and you can see the port where my finger is pointing. So pressure comes in, and pressure with nothing against the port will go through this port. This diaphragm is supposed to sit and seat against that port, blocking the valve when we want pressure, when we don't have a situation where the throttle closes and we've got to dump all that pressure very quickly. However, you have to remember there's pressure behind this, and so it wants to push against that diaphragm. How do we keep the diaphragm seated? That's where this spring comes in. It sits on top of the diaphragm, and then we have a cover, and in this case, it's just 3 screws holding the cover in place. So you can actually remove the cover and physically examine the diaphragm, provided it's not too difficult to get to. And if we put it on, I've already got my vacuum pump set up for vacuum. I'm going to apply a vacuum, and if I've done everything correctly, the entire system should come out, and it does. If the diaphragm does not hold a vacuum for whatever reason, then chances are there's a leak somewhere. And if there is a leak somewhere, then you know, okay, well, this might be part of the problem. The system is trying to release the pressure through the bypass system, but it's unable to do so because the spring is holding it in place, and the vacuum cannot overcome the spring tension. And again, there's our diaphragm, there's our spring. Now, if for whatever reason you lose the spring, I know what it's like to be a technician. We've got all kinds of parts that we save up for a rainy day, but this is a calibrated spring. You can't just go put another spring in its place. Okay, it is calibrated for the turbo itself and for the system that it's been designed for. Hopefully this gives you a little bit of a better understanding about bypass valves. And with that, Corey, we'll hand it back to you.
And thank you again, Mark. And with Mark showing that example there, it gives us a couple of things we can think about when it comes to diagnosing without tearing down or tearing apart. Again, it really leads to whether or not we have access. If we have access, these are some great things we can do that Mark was showing us. You know, it's unfortunate that we can't do this in every situation, but when you see an application where you can maybe do some of these manual tests or manual diagnosis process, I would encourage you to do it and keep yourself from spending a lot of hours tearing things apart. And generally speaking, when we have a condition where we want to do some of that testing, it's going to be one of a few codes that come up that's going to lead us to where we need to go and look. And those codes are typically going to be a P0299 where we have an underboost condition, or a P0234 with an overboost condition. And there are some cases with these types of conditions that we can find very easily with a visual inspection. And now real quick, just as a side note, we're talking about different things we can do to, try to help diagnose things quicker, things like visual inspections, things we can do manually. The reality is sometimes the visual inspection can tell us a lot more without having to go through a lot of diagnosis procedures. Now, on this particular vehicle, it was a 2013 Ford Escape. I was doing quite a bit of work to it. Had a lot of different issues, a lot of different codes. Buried deep down in all the codes that we were dealing with was a boost-related code, so I was going to worry about that one a little bit later. But we started working on other components, and then we were doing some test drives. And oddly enough, around 54, 55 miles an hour, it didn't matter how much weight you put on the accelerator pedal, that was as fast as it was going. It was not going to get any more power whatsoever. We were losing boost somewhere. We didn't know where it was, but we went back to that code, and sure enough, it's telling us, hey, you got an issue related to your boost. Now, in this particular vehicle, unfortunately, there was work done to it prior, and when that work was completed, there were some things left over. I'm sure we've all dealt with that before. A car that's come into the shop, it's already been worked on somewhere else, and somehow they ended up with extra pieces. Well, on this particular car, the extra pieces that weren't there, that they must have held on to, were all of the skid plates and engine covers underneath the vehicle. So the entire engine, transmission, everything was exposed to every element that could possibly be hit, run over, or shot up to by the road. Well, this solenoid for the turbo on the Escape, it really just sits. It slides in this groove down on a little arm that's on the turbo itself, and then it plugs in. So theoretically it shouldn't go anywhere, and in this case it didn't, which is nice. It can slip off, so that's one thing to look at. But what we found in the visual inspection cleared up basically the rest of the diagnosis on the boost issue with this one. And all it turned out to be, and it's going to be a little bit hard to see on there, but we had to mess with the hoses a little bit and start looking around, but something jumped up off the road apparently and hit our hose, splitting it almost in half. We've still got a little bit of hose left on this side, but essentially our boost could not work properly because there was a complete lack of sealing on this hose. So again, it's a side note, it's probably not something you're going to run into a whole lot, but when we come to visual inspections and things that we can do to more quickly diagnose, if we have an underboost situation and we look up and we see there's a lot of skid plates missing or engine covers or really any type of protection for the engine and transmission whatsoever, you might want to go look at these hoses first because there's a really good chance something has cut, nicked, or hit this, and that might be all that we have to replace is the solenoid itself. And again, in that situation, we're not going to have to take the turbo off. We're not going to tear the whole system apart. It's just a simple fix. And in some cases, as long as there's no damage to the solenoid itself, we can probably just replace the hose. It's a simple, quick, very efficient fix. Makes your customer happy, gets the car turned out of the bay a lot quicker. All right, so back to the presentation here. And so back to my point of talking about the visual inspection, in some cases, if we can access it, we can look and see, is the wastegate stuck open? Or maybe, do we have a leak between the turbo and the engine? So we may have an underboost situation that's just as easy as a visual inspection. Again, it really depends on how much access you have. Now, if we have an overboost condition, we may have a wastegate that's stuck closed. Again, that's one of those harder ones to look at because we're really probably going to have to get really into the turbo to see if it's staying closed and not opening back up. But we could also have control hoses leaking or disconnected. I showed you an example of that just a few moments ago with my own personal vehicle. It doesn't take very much for the hose to get cracked or leak or get torn, especially when parts are missing that are supposed to be protecting those hoses. And then obviously we can have a wastegate Fenton solenoid stuck in the vent position. So there's a couple different things that can cause overboost and a couple different things that can cause underboost. But at the end of the day, there's also a lot of things we can do to try to diagnose those without having to put hours upon hours of investment into it to figure out what it is. So knowing that, what happens to boost pressure if the wastegate hose is disconnected? Or so let's say we don't have control to that wastegate. Well, in theory, it's going to allow for unregulated boost pressure, which is going to be very damaging to a lot of different things. So to explore this a little bit further, we actually took, and we saw it on the bench here, the Chevrolet Cruze turbo, and we disconnected the wastegate hose on that Chevrolet Cruze and took the vehicle for a test drive. We'll see what that looks like in those situations. So we can see in the capture here that we've got the wastegate hose disconnected, and the technician has the gas pedal to the floor, and the boost pressure was over 38 psi, which is definitely a lot higher, about 12 psi higher than normal. But notice that the PCM has dropped the throttle position to just under 50%. Now, if we look at some other PIDs during the same condition, we can see something very interesting here. The boost pressure sensor was reading about that 12 psi, higher than the manifold pressure, right? And the boost sensor is going to be just in front of the throttle blade, and the map sensor is mounted to the intake. So what was happening here is that the PCM was effectively reducing boost by restricting the flow with the throttle blade. So in a situation where the wastegate's not working properly or the bypass is not working properly in some of these systems, the PCM can actually take over to effectively change other parameters so that we don't have that uncontrolled boost. Now, of course, if we reconnect the wastegate hose, we can clear the DTCs from the PCM, go get another capture, and we can see now, with everything hooked back up the way it's supposed to be, the actual boost pressure is now closely following that desired pressure, and then the pressures before and after the throttle blade are going to be very close. And so let's take what we've talked about so far and let's put it into a case study. Let's look at this in a practical environment where a vehicle was actually fixed. So in this case study, we're working on a 2012 Ford Explorer. It's a 2-liter EcoBoost engine. It's got 37,000 miles. It's really not a lot of miles, is it, right? So the concern from the customer was the check engine light was on and it had low power. So with that complaint, technician took a look at it, and obviously, yes, the MIL was on. And the other thing was the customer reported that there was a little bit of a rattle sound coming from under the hood. So obviously, we're going to do a visual inspection, and we're not going to see anything immediately. So we're going to try to duplicate that on a road test, which is what the technician did. And the technician did hear that rattling noise, so they verified that. And that was even at idle in this specific example. So went in, checked DTCs, pulled codes, and sure enough, there's our P0299 turbocharger underboost performance code. Now there was a subcode 27 where the fault was currently present. So we got a hard fault here. We know something is not working properly and it's right now. So we got to go do a little bit more digging, and we're going to look at the set code criteria here. And the criteria for this one is the execution for it would be continuous. So the monitoring duration is 5 seconds if the boost pressure desired and the boost pressure actual varied by more than 4 psi for 5 seconds. We're going to get this code. So we're going to go out and do some driving. And so the technician, knowing that this is a 2-liter Ford, we know this is a vacuum controlled wastegate, so they're going to go look at some specific data. The technician looked at the turbocharger boost pressure, that pressure before the throttle plate, and it was consistently about 9 psi less than desired. And then during the road test, couldn't find any obvious boost leaks. So this led the technician to think that it's most likely going to be an issue with the wastegate itself. So the technician did exactly what we did here. He applied vacuum to the wastegate vacuum actuator and watched the linkage move freely into the closed position. So he knows the linkage is working properly. So at this point, we're going to have to remove the turbo to determine if the wastegate is worn out or damaged. So we know that the rod is working, the actual actuator is doing its job. So what's going on with the wastegate itself? So unfortunately, we got about half of what we really wanted to do and what we discussed earlier with these helpful diagnosis ideas. But in this case, we're going to have to remove the turbo. And sure enough, when we pull the turbo off, the wastegate in the closed position had so much wear on the linkage. For some reason, at 37,000 miles, we already had so much wear on the linkage here, the wastegate would not fully close. So even though the actuator was working right, the rest of the system was working right, it was telling the wastegate to close. The wastegate was trying to close, but because of the wear, it would not fully close. Even when they applied full vacuum, the wastegate would not seal. So we're not going to have a properly functioning wastegate system when this happens. So, this is one of those scenarios where we did use some of these diagnostic processes that we thought about, and unfortunately had to pull the entire turbo off, but at least got us close. It at least gave us the reason to go to that customer and say, hey, we know what might be going on, but in order to verify it, we're going to have to remove this turbo. So obviously a new turbocharger was put on. You can see the wastegate is sealed properly off when the vacuum was applied to it. And then when we go and verify our job after the work and we install the new turbocharger, the boost pressure is correct and therefore power was restored. So in this case, again, we started out with a underboost situation, a P0299. We did have low boost in the test drive data. We verified the wastegate linkage was okay, took the turbo off, and we found that it was a worn wastegate. So in some cases, you can do as much diagnosis as possible without having to tear everything apart. But at the end of the day, you may end up finding yourself pulling a turbo off just to be able to fully validate exactly what's going on. And hopefully you don't see too many of these like this where the wastegate just won't close after everything else is working like it's supposed to. Now, before we wrap up, I do want to address a couple of questions I saw come across as we were going through this. A couple of different things that I think are probably things that maybe you're thinking of or somebody else might think of later on. And here's just a couple of my favorites that came through here. The first one is there an easy way to identify if a turbo system is always applying boost and has to be turned off, or is it always required to initiate boost when needed? It's a great question. Unfortunately, in this case, service information is going to be your best friend. There's really no catch-all. There's no identifying chart. Now you can go and look up certain Fords, like EcoBoost, for example, has a chart of all the different turbo systems that they have and whether they're on or off. So there's some things you can do, but again, that's going to be found in service information. So my personal preference would always be, let's get into that first. Let's check it out. Let's look it up. That's going to give us a little bit more information before we get into a further diagnosis. This one, though, I think is a really good one because we touched on it. We said that there are electronic actuators now. They're motor-driven actuators. We didn't really get into how they work as much. So the question comes up is on those new electronic actuators on the Ford turbos, what actually holds the wastegate closed? And the answer is it's the motor itself. So where we have a spring and a diaphragm on our pressure and our vacuum operated, if the spring fails, obviously, we can get a little bit of play in the shaft. Well, if the actuator fails, you're not going to get any play at all. It's just going to not work. So it brings up another really good point, and so that's why I'm glad this question was asked. Let's say the turbo's fine. Everything is working like it's supposed to, but we just have a failed actuator. Make sure, if you have to replace one of these actuators, you go in and you use your scan tool. Most of these are going to have a specific scan tool procedure that's going to make sure that they are adjusted properly. If that actuator is not adjusted properly, we're gonna have a lot of issues with the wastegate working properly and the boost in that system. So the answer to the question is, it is the motor. The motor itself is what's holding that wastegate closed. But again, if we have to replace one of those actuators, please make sure you go in and do whatever calibration is required through the scan tool to get that adjustment done properly. All right, and with that, again, I want to thank everybody for joining us today. Obviously, that was a lot of information, very fast, and if we really wanted to, we could spend hours here deep diving turbocharger system, wastegate system, bypass systems. But if you do want more resources related to turbochargers and some diagnosis process, installation process, and some just general information, don't forget to check out our YouTube channel, the Standard Brand YouTube channel. We've actually got a full playlist of different things turbocharger related there. A lot of great information from a lot of great technicians and trainers that put together some great content to just help you keep learning more and more about turbochargers. And then obviously check out standardbrand.com, where you can actually learn about our turbochargers that we have in our system, the turbocharger kit like you saw on the bench here in the beginning for the Chevrolet Cruze and everything that comes with it. And there's also the catalog on there and a lot of information around all categories that Standard provides. So again, thank you very much. We appreciate you being here, and hopefully we'll see you next month for the new Power Hour coming up. Have a great day, everybody. We'll see you.